All right, let's talk about the absolute value function defined for hyperreal numbers. We talked about last time that the absolute value function is a piecewise defined function such that you get x if your value is greater than or equal to 0, negative x if your value is less than 0. Then we discussed, what does this equal? What do we determine that equals? Why?
There's a little omega that's on a higher level.
Because little omega to the first power is on a higher level than little omega to the second power. This negativity is negligible. Just like most people's negativity in real life, your negativity, make it negligible. Okay? Stay positive. That's what the absolute value is for. Okay? Moving on, let's do some examples. Let's see whether you really have mastered this concept. What about here? What do we get here and why? You're stating that we get 38 minus 15 omega?
Yes.
Why?
Omega, like nothing compared to 38.
Yeah, it's on the lower level. This is on the real level.
Yeah.
This is on the omega to the first power level. So you're absolutely correct. What about something like this?
Thing,
Why?
because 5 is in the real level.
And why does that give us the same thing?
All the other ones are on lower level.
Then pi, yes. Okay. All right, what about this?
Stays the same.
Why?
In omega to the power of 1 over 3 is like the highest level,
Mm-hmm.
and all the other ones are lower.
And it has a positive sign here.
Yeah.
So the overall absolute value becomes positive. What about this?
Same again,
Why?
because capital omega, the first power is higher on the level than negative capital omega to the half power.
Okay. What about this?
When they flip now,
Say what?
when that, because capital omega to the third,
Capital omega to the third is what?
the highest power ends at negative,
So
so you would have to multiply everything by negative.
the whole thing or just one of these?
The whole thing.
The whole thing. Very good. The whole thing is endowed with a minus, and we must ensure that it distributes to all the terms. So make sure you distribute it. Notice that when you distribute it, it equals So that is what it equals. Now, let us do problems where we approximate. Okay. So what about our old friend 38 minus 15 omega? You guys, what would you say this equals? We've done it before, right?
Yeah. No, you would change it. Maybe.
Yes. I didn't say whether it was capital omega or lowercase omega. I said omega. So you recognized astutely, and you see new, but you're probably not new. You're just now in real life.
Yeah. Okay.
You were imaginary, and we took your complex conjugate. You guys get it? If you have an imaginary A plus BI, the complex conjugate is A minus BI, so that when you multiply these two values together, what you end up getting is A squared minus B squared. So something that has complex values or imaginary values becomes real. Yes, now you're real. So you're saying that we got to put a minus sign out here? Which then equals. So what does this approximate to?
15 omega.
Why?
Because the other one is too small, so it's kind of like nothing.
Yes, it's kind of like nothing compared to that 15 omega. Now that you're getting the hang of it, as always, us mathematicians are easily bored, and we like to up the ante. We get bored very quickly, and we want to spice things up a little bit. So let's invoke fractions here. This equal and why? I'll give you a hint. Because we're saying equality, we have not done any approximations yet. So I'll give you the denominator. You give me the numerator.
It's negative omega plus 8 omega to the second power.
Ah, you're getting that because you're doing this, right? Putting the negative on the whole thing so that when we distribute the negative, we get this. So now let's approximate. The numerator and the denominator approximate to what?
Denominator is 4.
Very good. We all know why now. What is the numerator?
8 omega to the second power.
And omega squared. So, what does this equal? All right, are we done?
I want to see it.
Yes, within this realm, we are done. Within this realm of approximation, we're done. Okay, so let's move on to a different realm. Let's move on to section 1.3, hyperreals and functions, where we're going to talk about what happens after this. What can we do after this right here? Because what we aspire, if you can think of a function as a machine, so far, we're getting real inputs and getting real outputs, all right? For example, f of x is equal to x squared minus 5. Well, f of pi squared minus 5, right? We put in a real number pi, we get a real number out, pi squared minus 5. So what we want to do is also include hyperreal numbers. How can we get away with that? Well, it's because the hyperreal numbers actually exist within the real numbers. Least you forgot. Right? They're actually stuffed in there. Just like the real numbers are stuffed in the infinite omegas. So because the hyperreals at the lower level are actually contained within the reals, we may evaluate real value functions for hyperreal values. Furthermore, that correlates to exactly what we stated was the transfer principle. So the transfer principle says that this is possible as well. Meaning, we can have this, but we can also have this. Right? So for example, what is f of omega plus 2? Well, that's omega plus 2 squared minus 5. So this becomes omega squared plus 4 omega plus 4 minus 5. So this becomes omega squared plus 4 omega minus 1. So take a look, we're evaluating a real value function for hyperreal numbers. You just treat it like we always have treated it, as really none of the rules change. Now, let's say we have something like this. I want to evaluate something like this. Notice that this ends up equaling right? So when we combine like terms, omega squared, goodbye. Omegas, we have a minus on omega, goodbye. 9 with 21, well, 9 with 21 with 1 is just negative 20. Then we add a positive 9 to that, what do we get? Very good. So f of omega plus 3 equals this. Now, what does this approximate to? First order approximation is what?
Oh, it would be minus omega minus.
Yes. First order approximation is that. When you do another approximation, we get this. You might jump from here to here. Don't forget that this is actually happening. So what about like, and let's evaluate something like this. Right? 3 copies multiplied. So when this is times that, we get omega squared. This times that, we get a positive omega. This times that, we get a positive omega. This times that, we get a positive 1. Combine like terms over here. Then we do a distribution. What this implies is we get this. bringing that calculation over here, we get negative omega cubed minus 2 omega squared minus omega minus a omega squared minus a 2 omega minus a 1. So the negative omega cubed term comes down here. We combine the squared term, so we get a negative 3 omega squared term. Our negative omega terms combine to become negative 3 omega minus 1. So this is what our f of negative omega minus 1 equals. What does this approximate to? First order approximation.
Negative 30 omega squared is 3 omega.
Very good. Second order approximation.
Negative
Third order approximation.
negative 1.
Fourth order approximation.
-1.
Ah, yeah. Yeah. Fifth order approximation. Right? This is just the highest level on out of all these, it's the highest level. So if we continue to iterate the approximations, it will stop at the highest level. Now, being at a high level is a relative term, right? Being at a higher level is relative. This -1 is really just a big fish in a small pond compared to omega. Or omega squared, right? Relative to the terms inside the expression, it is at the highest level. Big fish in a small pond, really. So, let's talk about the 3 R's principle. So, initially, let X be a hyperreal number. This is the first thing that we do. So, if X is 0 or X is infinitesimal, infinitesimal, this is what we get. This arrow means this is what the implication is. If this, then it implies this happens. Okay. We say that X renders the real result 0. When you see a dot up here, it means renders the real result. Or actually, yes, actually we want to keep that real part. Because recall, what we aspired to do was create a situation where we have functions, we have inputs, either real, hyperreal, but they output reals. Why is that we want that? Well, it's because we like functions that behave this way. They have very useful properties that we have proven a lot of theorems for. So that's why we want to do it. We want to create our theory. We're going to create the theory in which it abides by this so that we can utilize all the tools of real analysis. Okay. What about number 2? If X is approximately a real number such that R is an element of the positive reals, for instance. What does it render? Well, it renders the real result itself. So this was an example of that right there. You know, this was a hyperreal number, and we approximated our way to it here. For example, omega. Omega renders the real result 0. Because, look, omega is approximately 0. That implies it will render the real result 0. Number 3. So if, and I forgot if right here, but it's implied. If x is approximately a, where a is an arbitrary infinite number. Remember, we defined alpha to be an arbitrary infinitesimal, and when we defined capital Alpha, which is our normal English A, which actually it's also the same for Greek. That is an infinitely large number. This is an infinitely small number. So if x approximates to an infinitely large number, what do we get? We get that x renders the real result plus or minus infinity, where it's plus if x was positive and minus if x was negative. Make sense? So this, why do we have a dot here? Because it's different than equals. That dot is there to show that it's different than equals. Equals means it's truly the same thing. Approximately means they're nearly the same. The difference between them being the same is very small. And what does this mean? Well, this ensures that after our function is done, after we're done evaluating the function, we plug in values to a function, evaluate. At the end, it ensures that we don't end with this. Because our functions, we don't want them to output hyperreals, we want them to output reals. So it ensures it actually ends in this. Because this whole thing, let x be a hyperreal number. So this thing right here is a hyperreal number. If x is 0 or infinitesimal, it renders the real result 0. But it's not 0 or infinitesimal. This -1 prevents it from becoming 0. If that -1 wasn't there and we had a bunch of omega stuff, this whole thing would render the real result 0. But it doesn't. It's in case 2. If x is approximately a real number, as we found it's approximately -1, then it will render the real result -1. So we could have said all of this stuff renders the real result -1. Furthermore, if we had a situation where we had a capital omega here and x approximates an infinite number, whatever the sign on the highest order capital omega was, that is what we would render it as a real result towards plus or minus infinity. Notice that infinity is not a number. Infinity is a concept. So we can't say this equals infinity because it's a concept. You can't equal a concept. You can only equal something that's discrete, an actual tangible entity. Okay? So we have to create a new kinds of equals as rendering the real result. And we can think of the real number system as R. Additionally, we can add the hyperreal numbers, tiny hyperreal numbers in here. And then we can actually invent something called the extended real numbers. Where in set theory, it would be R union plus or minus infinity. This is all like higher level math language that I'm talking to you about. So you're not expected to know the extended real number system and all that. You don't have to know that. Don't worry about it. Okay. I'm just showing you what's going on. So you're not like, why are we doing this? Or what is the framework for all of this that you're talking about? I'm laying out the framework so that you understand that it's not just kind of throwing it up in the air and I hope it makes sense. No, we throw it up in the air and we make sure it has a parachute and it's falling onto a trampoline. Okay? So it's a controlled throwing things up in the air. Okay, so that's the 3 R's principle. I'm going to delete it because I need more real estate up in here. Well, let's utilize the 3 R's principle. Okay? And in doing so, what we want to do is adhere to the process called EAR. Stands for evaluate, approximate, render when evaluating functions for hyperreal inputs. For example, yeah, what about this? What does this equal? It equals this, which equals 4. When this is multiplied times itself, it's a 4. This multiplied times that, it's a positive 2 omega. This multiplied times that is a positive 2 omega. That multiplied times itself is a positive omega squared minus a 4. Yes, the 4's cancel. Can everybody see? Okay. And then these two combine to give me a 4 omega plus an omega squared. Okay. So that was the evaluate. We evaluated the function at the hyperreal input -2 minus omega. What does it approximate to? Okay. First order approximation is 4 omega, right? Technically, what is the second order approximation? Yes. Why? It's the highest. There's no real number to say, well, compared to this real number, it's approximately 0. It's done. I can do this again. Does that make sense? That's a really like important concept to like really sink in. If there was like a +2 here, then of course, all of this would approximate to that 2. But it's not. The highest level term is this omega term. So it approximates to this 4 omega. And then if you try it again, no, it just goes back to 4 omega. There's nothing to make the hyperreal value go away. So what do we have to do? It's that whole render the real result concept. This is why we had to invent it in the first place. We had to invent the render for the hyperreals to surrender. So what does this render the result as?
0.
Why? Yes, it renders the real result 0. because it's a very tiny number. So compared to the reals, it's 0. Rendering the real result basically compares whatever value you get after you evaluate and approximate to the real number level. It's like approximating it to that. So this render the real result thing is like, compared to real numbers, how big is this? Tiny. That's how you think about it. Here's another example. What is this? Well, this equals, that equals, this equals, this equals, when we combine these, make these cancel, it becomes a 3 minus 4 omega plus omega squared. Now, that was the evaluate. Let us approximate. What does this approximate to?
3 minus 4 omega.
That's right. That's why I wanted to have you all highlight that this is a first order approximation, second order approximation. Because if we went to second order approximation, we'd go straight to 3, right? So now we approximated. Now when we render the real result, what does this render the real result to? 3. Because if you go back to the definitions of the 3 R's principle, it said if a hyperreal number x is approximately a positive real number, that means it renders that result to be R. Here, our x is our 3 minus 4 omega. 3 minus 4 omega is approximately 3. So we say that it renders the real result 3. What about this one? Let's evaluate it. Let's see what is f of 1 plus alpha. Recall, alpha is an arbitrary infinitesimal. It's arbitrary, meaning, it could be omega, but it could be omega to the 4th power. It could be omega to the 17th power over 27. Any arbitrary, infinitely small number, to whatever degree. It could be you get the point? So let's evaluate it. Okay. So then this combines to divided by, this becomes a minus 3. So it becomes 2 alpha plus alpha squared minus 3. Okay. Now recall when we have fractions, we want to approximate the numerator and the denominator separately. So what does the numerator approximate to? What does the denominator approximate to?
2 alpha minus 3.
Very good. All right. Now what? What does that approximate to? What does 3 approximate to?
3.
What does 2 alpha minus 3 approximate to?
Minus 7.
Yes, and I won't ask you to tell me the reasons anymore. So this whole thing, we can extract the information that it somehow equals a -1. Evaluating 1 plus alpha into this function gives us that it equals a -1. But what if we had evaluated at 1, not 1 plus alpha? Notice what happens. So what was the point of this 1 plus alpha business if evaluating at 1 gave you the result -1? The shrug of the shoulders. In terms of evolutionary biology, human beings invented that form of body language to protect their throat from incoming damage, like from a spear or arrows. That's why we shrug our shoulders when we don't know, or when we just don't know. We feel like our environment is sketchy, so we shrug our shoulders to defend our neck from being pierced from a rock or an arrow or spear. But there's no rocks, arrows, or spears. You just have no idea, right? So as default, we go like this. And now you know why human beings do that.
That for real?
Yes. That's for real, yes. So you don't know why, huh?
No, sir.
You're gonna find out why. It's gonna have to do with avoiding dividing by 0. Notice, you know what? Since I just brought it up, I'm gonna have to do it for you. Because why would I wait? We're talking about it right now. Why would I wait? You know, orders of things don't matter to me. Right now you're really interested. I've piqued your interest. Why not give it to you now? Making you wait for it, you might lose interest. Especially since you kids are always on your phone, and you like zone out anyways. Got the attention spans of a goldfish. And I force you in here to actually pay attention for longer than 5 seconds at something. It's not your fault. Actually, all human beings in society are having lower attention spans as a consequence of advertisement and TV and videos and snapgrams and Instachats and Pokemon. You're all busy playing Pokemon. I'll stop getting on my old man rant. What would occur if I evaluate this function at 2? What do you guys think is going to happen? That happens, right? So what happens there?
0.
So what does this equal? Undefined. Were you virtually there when I proved why you can't divide by 0?
Yeah.
Yes. It's undefined, not because I say so. It's because I showed you why. There's actually logical reasons for saying we can't divide by 0. Because assuming we can leads to logical inconsistencies in the mathematics after algebraic operations. So we can't do this. Question. What do we do? What do we do? This is why this is exactly why we invented the infinitesimal numbers. It's so we can evaluate it at almost 2. Infinitely close to 2, but not at 2. Because it's at the point 2 where the function messes up. So why don't we evaluate it just a little bit to the left? Or just a little bit to the right? Which one do you want to do? A little bit to the left or a little bit to the right? You want to do a little bit to the right? Okay. A little bit to the right of this is it not? Alpha is a very tiny compared to any possible real number. So it only scoots what 2 is by an infinitely small amount. But guess what? It will make an infinite amount of difference. Notice what happens here. Right? So on the top, we get 4 plus alpha. This becomes 4 plus 4 alpha plus alpha squared minus a 4. 4's cancel. So this becomes 4 plus alpha divided by 4 alpha plus alpha squared. What now? What now?
The approximate.
Say what?
The approximate.
You could. Well, you could also factor, can't you? Can you factor? I know. I know. Notice that these cancel. So you get 1 divided by alpha. So we were able to extract information about the function. It equals 1 over alpha instead of undefined. Of course, what is 1 over alpha really? This is your A, an infinitely large number. But it allows us to circumvent the fact that we were not able to evaluate it at all. Right? This is very important. This is revolutionary, actually. When this was invented, it was revolutionary. This is the concept that's behind calculus. Calculus allows us to evaluate functions basically at the point in which we can't evaluate it at. It solved the problem of what happens when we divide by 0. Except we don't divide by 0. We divide by something really close to 0, but not 0 itself. That's how you got around the problem. This is the concept behind calculus. What about if we evaluate this function and we call it equal? This is what the function originally equaled. What about f of alpha? What does this give us? Well, it equals this. Right? And what does that equal? I'm a mathematician, so I like to factor. Again, when human beings discovered how to factor, it was a revolutionary idea. It allowed us to solve polynomial equations for their roots. What people don't get is this is thousands of years of human efforts and knowledge that we're talking about here. So this is some heavy, awesome, cool stuff. It's the fruits of humanity's labor over here. So we get 1 over alpha minus 2. What does this approximate to? 1 approximates to what? 1. Alpha minus 2 approximates to what? Yes. So compared to f of 0, because just f of alpha is as if you're evaluating at f of 0, but not. But look at what happens. Interesting. So what's the point? What was the point of doing this more complicated thing versus this simple thing? Well, it's the details here that allows us to solve this impossible problem. I always like complicated things more than simple things. Especially as a child, I always liked things that were complicated and not very simple. We're all like that when we're born. We enjoy complex things because there's so much detail that you become enamored with all of the detail. Like, what if they had a painting and the painting was just like a dot on a white canvas? Just one dot. Looks like someone splashed some food or some oil while they were cooking some scrambled eggs or something like that. It's not very cool. But when you see those paintings with all the detail and whatnot, human beings like that, you know, where there's all these details and you zoom in and there's more details. Stuff like that excites human beings. And you have to retain that intrinsic curiosity because it's these extra details that allows us to discover new truth about mathematics. And mathematics is the study of truth. Mathematical truth, that is.
So do you know who actually broke the little, like the code for not for us being able to solve without using 0?
So ask that question again.
I said, do you know who was able to like actually basically make it make sense to where we can't use 0 and we would have to use alpha instead?
Yeah, Sir Isaac Newton and Gottfried von Leibniz are the historical individuals that are given the credit for it.
Okay.
It may have been discovered earlier.
I knew it was Newton, but I didn't know who the other person was too. We just talked about it in physics.
Right, Gottfried von Leibniz. It may have been discovered earlier. It may have been lost to humanity, but then got reinvented. It could have been discovered earlier. Ooh, lost city of Atlantis, man.
How you playing? It really might be something.
There might be, you know, who knows? Yeah.
There's a lot we have not discovered.
That's correct. That's correct. Well, we're kind of out of time here. And let's see. Yeah, we're very near ending this section. So because we went over the syllabus, seems like we're always just a little short of completing a section. So what I've done is offset that with when your assignments are due. Remember that 1.2 got extended to when? Friday, coming up. Okay. I will assign this, and I will assign it for not a week from today, but a week from Wednesday. Sound good? Okay. Because it's not fully complete, even though we're almost done. I want to give you enough time to absorb it and understand it thoroughly. Okay?
Remember the question I have for whenever I try to go back to look at the Zoom video, X or access code.
Yeah.
What do we form something like that?
All that information is on the announcements. It's also on my YouTube channel,
Oh, yeah.
which I've linked on the announcements.
Yeah.
Mhm.